So that's true.
Are you feeling better?
Yeah. I was just like busy for some reason. Thank you. All right. So I think we had some requests. Okay, so we had a request for a neural network and for extracting the templates. Okay, that's from one person, and we had Dijkstra and A star. Are there any other requests before I do the long things?
If you have time, I think there was a couple of other stuff in the AI slide deck.
Okay.
Like the need to know and like the implementations.
Okay. So well, that's like in the same kind of vein. Okay, all right. So since we had like any requests from you guys?
The same.
Okay. So that's what everyone wants. Okay, all right. So let's do that. So basically, so I think the first request was for a neural network. So let's do the neural network. So what I'm gonna do is kind of the most straightforward thing, which you would just read off the slides. In practice, people use like linear algebra, which I'll mention briefly, but won't. Well, maybe I'll do it. We'll see how it goes. Okay. So we are in, I'll just pull up the slide so we can read off of it. Okay. So basically what we want to do, well, I think what I was asked to do is to take this slide and just implement it in code, right? Mm-hmm. So basically we need this function. So the sigma, I did not specify it on the slides. I'll do a formula for sigma. There's like various ways of doing it. So I'll just get that out of the way. So the shape, so this is there was a picture on one of the slides. So this is the sigma. So if you look at, so there's multiple possible formulas, right? But basically if you look at it, it's like if x is super positive, then this is basically zero. Right? Because like exponent of like a big negative number is just basically zero. So for very large x's, this is 1. And then if x is super negative, then this is a very large number. So the whole thing is basically 0, right? So like it's 1 divided by a very large number. So that is how it's this kind of shape, right? With x negative, it tends to 0. With x positive, it tends to 1. Okay. So, but basically you can think of it as like a monotonic transformation, right? So it's still just like big, like larger numbers get mapped to larger numbers, smaller numbers get mapped to smaller numbers. So, okay. So now we want to compute this. So I first need to define a W and B. So the easiest way to do it is to just define them as NumPy arrays. So here W is going to be So if we look, so if I look here, this is always 1, and then this can go, this is of dimension 4096, and this is of dimension 6, right? Does that make sense? Because we have, so what are the W's? The W's connect the X's and the Z's. There's 4096 X's and there is 6 Z's. And then the 1 is just always there. So this is 1 times 496.
So what does the 1 stand for?
Say it.
What does the 1 stand for?
So later slides, this would vary as well, right? So, but this is basically like nothing. It's always the same. It's always the same dimension. On the later slides, when we have a hidden layer, the way the W's work is the W's that connect the X's to the H's are all like W1 whatever, and then the W's that connect the H's to the Z's are like W and then always 2. And then whatever.
So the 1 is like the first layer.
Yeah, exactly. Well, so like the thing that connects the input to the first hidden layer. Yeah. Yeah. Are we good with this? All right. So I'll just initialize it, and I'll initialize it as just a random matrix of this size. So B is of size 1/6. Right. So we are still implementing this, right? So here there is 6 B's, so like 1 B that corresponds to each set. So this is not the right form. So this is the one, right? So here, in order to compute Z1, you do a dot product of those guys plus the B. Right? Does that all make sense to people?
So you just remind repeating that.
Say it?
You just mind repeating that.
Yeah. So when we are computing, for example, Z1, what we do is this slice of W dot X plus B11, right? So to compute Z1, we use B11. And to compute Z2, we use B12, and so on. All right. So if we need to do the computation, what would we do? So let me do it with like a for loop, and then we'll do it with a dot product. So Z1 would be sigma of the sum of W 1 J A 1, I guess, times, I'm sorry, 1 J times X J plus B1, right? So something like that. Is that making sense? Okay.
Can you
So
explain why Z1 is that again?
Y is,
Like in the graph, why is B11?
I'm sorry, I can barely hear you. Let me try to plug in my headphones. Maybe that's going to be better. Yeah, can you try saying it again?
Yeah, why is B like 1, 1? Like, what does this mean? Is it like a dot product?
Okay, the question is whether this is a dot product. So this is a dot product, right? This is just like coordinates.
So B is just a constant.
Yes, B is a constant. Or, I mean, like it's, whatever B is. We're just saying, like, we're basically just implementing the formula over here.
Okay, okay. I see.
Yeah. All right.
So, okay. So that is for every Z. So I can just now initialize the Z to be all zeros. This. And now I'll say, so the Zs are indexed with K, I believe. And then, so a NumPy allows you to just take Z and transform it with a sigma after that. Does that kind of make sense? So like all I'm doing is just like implementing sigma with a for loop. And then I'm computing it 6 times because there's 6 Ks. Yeah.
Why the summation we were using Z0K, but above in your comment, like the.
Yeah, so this is just because like in Python, so I mean, like the question was, is there a reason? And the reason is that in Python, the indexing starts in 0, but in math, it usually starts with 1. So
Your comment might be 1 and then K, it doesn't make a difference whether we use 1 or.
and not really, yeah, so I kind of just translated it because like in math, you don't ordinarily start with 1. So it's also like, like when they say in range 4096, it really goes up to 4095 because it starts from 0. Okay, so that's one way to do it. So we also, of course, need, so here X is underlined because I didn't initialize X. So X, if I have one X, it would be of size 4096, right? So that just creates an array of size 4096. So that's one way to do it. So another way to do it is instead of doing this, which is basically a dot product of the slice of W where this could go this could be anything. We could do it with a dot product. So I can say Z 0K is like this. Right? So in fact, so that's not something that I want to pay too much attention to, but this whole thing is actually matrix multiplication. So you can actually say directly something like this. So I'll change this to, so dot NP dot is matrix multiplication. Like if you think about it, you don't have to right now, but this is basically just multiplying W by X. Yeah.
What's a colon?
So colon means everything, right? So so if you so if we define W like this, too large, so I'll do like 10. So W looks like this. So I can say I just want 0 and then everything here and then dimension 1 here, and that will get me W001, W011, W021, and so on. Okay. But really kind of like what we were talking about in terms of like the basic implementation is just this. Okay. So this, of course, like W and B here are just random numbers, so it won't compute anything that's too useful. The idea is that you can, like we did with the polynomials, you can make it so that it outputs the things that make sense most of the time by adjusting the coefficients W and B. Okay, so I think there was also a question of extracting the kind of relevant slices of W. So one way of doing it is literally just this. You can also do it manually, right? So you can say like extract template for person at index 2. And we could initialize it, or we could just say this is just empty, and then, for J in range, we'll append 0J for every J. Right, so this is, so basically template would be does that make sense?
Did you ask to do this in C or just in Python?
Yeah, so like people ask me that on Piazza. So like, look, I'm not going to exclude the possibility that you could ask to do this in C, and the reason is that it's not impossible to do, right? Because essentially you have some way of storing an array, which we definitely know how to do in C. And then it's kind of like simple manipulation of the array. At the same time, it's combining two things. So in that way, it might not be an ideal question if you are looking for a straightforward question, because you're combining like both knowing how to write in C and kind of knowledge of the external algorithm. But other than the fact that you're combining those, like it's not difficult to do in C, I would say, or like there's more difficult things. Yeah.
Professor,
Be the question you asked on the exam or contest to code this.
So for example, I might say assume that W and B are given like this. And given that we haven't seen np.random, I would have to say that like this is what np.random does. And then I would say here is a graph that represents the specific neural network. Compute the output sets. Compute the output set.
Oh,
Professor,
Yeah.
in this code, W is still
Sorry, I still
random,
can't hear you. Hold on.
right? So, hello?
Yeah, sorry, go ahead.
When you're finding the template for number 2, W is still a random matrix, right?
Yeah. Yes. So here, so the question I think was, when I'm extracting the templates, are those still random numbers? And the answer is yes, they are. So the way so like maybe I got lucky with the random number generator, and those are for some reason good templates, but ordinarily, of course, they would not be.
But like in the actual case, we need to like tune the W's, right? Before doing that for the template.
I mean, you can extract the templates at any point. It's just that before you tune the W's and the B's, they're probably not meaningful. In fact, very likely not meaningful. But like I did that because people asked me to. But you're right that if you like all I did was generate random numbers and then extract random numbers from the array, they would still be random.
Okay, yeah, thank you.
Professor, I have a
Yeah.
question. So like,
I'll repeat the question for you guys. Yeah, go ahead. Yeah.
so like, are things like B and the weights, will they be given?
So the question was, would something like W and B be given? So I could, in principle, ask you to input them yourself in some way, or I could give them to you. So I could imagine saying, read them from a file or something, or
Okay. Oh,
or
okay.
I could imagine. So of course, like in a pre-specified format. Or I could imagine saying, like, tell me, because there's multiple ways of doing it, right? So I could just say, pick a way of inputting them, like here. So another kind of example of a question. If I keep giving examples, I'll give all of them away. But anyway, so an example of a question might be, here is a neural network. And so this one is too big, but like if I give you like concrete numbers, and then I could say, okay, like I literally have given you the concrete numbers, like make it compute the thing.
Okay. So also like just like something in general, like all the W's and stuff, like you basically decide them when you're training the neural network.
Yeah, so the question was whether W's are decided when you train the neural network. Basically, yes. So the training process is the process of adjusting the weights and the biases B in such a way that the output is good in some sense. So that's not something that we've done in detail.
Okay, thank you. I have like one last question. So when you say like we need to be able to implement like a graph representation of the neural network, like is it possible that you like show us like an example?
Did they say that?
Oh, sorry, like yeah, I think on a slide above.
Where?
Oh yeah. Slide 15. It says like set up a graph that represents the neural network.
Oh, okay. Yeah. Sure. Yeah, so kind of what is meant by that is just like, here's a picture, understand that it's a graph, and code it in somehow, right? So what you could say is something like, so you would have to implement some kind of graph, right? So there would need to be a node. So that seems like a reasonable way of going about things. So we have name and we have, edges and stuff. Okay. Right. So now what we need to do is create the neural network. So I think here the edges are unweighted, so we would need to add a weight here. Right. So by the way, like it's all on YouTube, like the way I recommend doing things. I mean, you can type it in, but also like in the interest of time, I am using autocomplete. Like you can like do a screenshot of anything at any point and just plug it into ChatGPT, it'll give you the text. So that's like one way of doing it. So okay, anyways, I'm creating the graph now. So here, what I'm gonna do is I'm gonna create like those x's, and then I'm gonna create the z's, and then I'm gonna connect every x to every z with its own weight. So I'll create this, and the name is gonna be like x I. Seems good. Do I need the value here? I don't really need the value, just have a name. Okay. And then I'll do here, that would be z's. So I need to store all of them, right? Because I need to access them somehow. So store them just in a list. Like this. I'll rename this to K. And now I need to hook all of them up. So I need to compute the random weight, and I'll also hook it up to ZK, even though like, so like if it's a graph, like if I want to get from Z to X as well, sometimes you need to, then I guess I need the two directional edge. So it's going to be like this. So this is more a question about graphs than it's a question about neural networks, because like all it is just taking this picture and representing it as a graph.
Professor?
Yeah.
Sorry, is there any practice problems about like the neural network?
So yes. So like I mean, I think not in the sense that you're asking, but if you do every need to know slide, then you should be good up to kind of implementation details that are not really about neural networks, but really about graphs. So if you do like the graph practice problems and you do kind of the neural networks need to know slides, you should be good.
Is there like a sample problem that you can give us?
Yeah, so if you like I kind of did, right? So the example that I was just doing before, so the example over here, was in response to a sample problem, right? So the sample problem was implement the neural network on slide in slide 16. So that would be kind of the problem that corresponds to this, right? So in the same way, so like hopefully that makes kind of a little bit more sense, right? So in the same way, like if you look at other need to know slides, so here you have like 1 nearest neighbor algorithm. So again, like the practice problem would be assume that the input is given in this and that format. So for example, the input might be given as a list of lists where each list is a tuple with the pixel values and the name. And what you need to do is implement the 1 nearest neighbor algorithm in order to get in a new input that's a list that corresponds to pixels and get an output that corresponds to the name, right? So this is not a need to know slide. This is a need to know slide. So here, so this is more like, like need to know this. So that means that if you're given, for example, this kind of code with a hidden layer, then you should be able to take that code and output the images that activate a given hidden neuron the most. And like all it is just you compute the hidden neuron and then you look for the inputs that make it the highest.
Okay, thank you. Also,
right? So it's not really a situation where there so this is not a situation where I can give like a lot of practice problem solving problems just because we haven't done very much, right? Like all there is basically like literally the things that are on the slides, and then the only possible variation really is just specifying like here's the input format, so work with that input format in order to get the output.
okay, yeah. Also, will reading files be on the test like in C again? Because like it's on midterms, but like it never showed up in previous exams.
Sorry, I missed the thing you were asking about. Can you start from the beginning?
Will reading files be on the exam?
Reading files. So if it is, you are given kind of the C functions on the handout for reading from files. So to the extent that we've read from files with fgetS, yeah, you could get that, yeah. So like to the extent that we've done it, so we haven't really done it in lecture except as an introduction to the labs, right? So to the extent that we've done it in the labs, sure, why not? But the only way we read from files is with fgetS. Does that make sense? Yeah.
Great, just to repeat for this one, you said basically just like compute all the outputs of the hidden layer and then find the input that gives the highest output.
Yeah.
is that like the highest output of like a particular node in that graph, or like of like all the nodes?
Of a particular one, right? So if you remember the way it works to visualize kind of the job of the particular neuron is you're saying like that neuron for which input is it the highest, and then this is the visualization of that. So like those 9 images activate one particular hidden neuron the most. So activate means, its value is the highest.
Okay, so like in like the specific case, we had an input that was like dog stuff looked like the one in the square in the
Right.
top left, then it would activate that one the most.
Yeah.
Okay.
Yeah. Yeah. Anything else? All right. Okay. Yeah.
Professor, can you show how to do the hidden layer, like the implementation?
I'm sorry, I'm hearing like about 50% of what you're saying. Can you maybe type in the chat?
Okay.
Yeah, I'm sorry. I don't know like if it's on my end. There you are. Sorry. Yeah, so the answer to this is yeah, I would have to give, like, if you need it, I would have to give it to you. Yeah. Okay. Okay. So show the implementation of the hidden layer problem. I guess. To compute the hidden layer, what we would need is basically more W's, right? So there would need to be, let's say that we have 2 W's, and let's say that we have, so 2 sets of these, right? So like essentially here, you would now be able to say like W0, blah, 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 and also W1, blah, blah, blah. And the same for B, right? So with this, now we'll compute the H first. Oh, sorry. So here, this is not quite right. We'll do it like this. So we'll have one. Yeah, okay, that doesn't really work well with the slides. So now, like I just want to like have a hidden layer. So what we'll do is we'll do the same thing as before, but first we'll compute the hidden layer, and then we'll use the hidden layer as the input, and we'll compute the sets, right? So here I'll do for K and range head. And so this is kind of the same thing as before, except I'm computing the hidden layer, right? So hopefully it's okay to autocomplete. And then I'm doing the same thing again, and I'm computing the Z using W1. Okay, does that make sense to people? need to define the Z.
Professor, what is N hid?
So this would be the number of hidden units, right? So if we have a neural network with a hidden layer, so we compute the H's in the same way that we computed the Z's before from the X's, right? So it's again kind of this nested loop where we compute the H's for the dot products. And then we just treat the H's the same way we treated the X's before in order to compute the Z's. Makes sense? And then here we have, so here the notation is capital K for how many of the H's there are. And that's something that you just get to decide. Okay. So the only thing that's missing here is sigma. And then we compute this. And then we do sigma. Okay. So now that's kind of the raw code. So if I want to actually compute the hidden layer, I would need to like compute it for multiple x's, right? So the way I'll do it is I'll just define it as a function. This. So I'll move the W's and the B's outside. So all of that is going to get taken out over here. And here, what I'll say is, okay, so after I'm done, I'll return the Z, and let's say I return the head as well. And is that making sense?
Is it possible? This,
Yeah, I'll post it, yeah. Or do you want it like now?
like, yeah, whenever
Okay.
you're done with.
I mean, I can do it now. Okay, so you can just look for, so I'm not going to like email it to everyone because that's just going to confuse people. You can look for like April 11 on Piazza. Yeah, like the reason I'm being kind of slightly sloppy with this is I kind of like I'm just doing what's being asked, but I don't like there can be like so many variations on this. So certainly like if you feel like it's useful to kind of go over this could absolutely be useful. At the same time, like you can define those in kind of multiple ways, right? And all I'm trying to do here is just get to the point which I'm already at, where I can compute Z and head. So now that I can do it, so I'll need to define like some kind of axis on which to try things. So let's say that I have like 10,000 x's that are all of this size, right? And now what I want is like, let's say for hidden neuron 7. So what I did, so I can just compute the activations for neuron 7 for every one of the axes, right?
Sorry, so the
Yeah.
hidden neurons are just the same as the hidden units.
Yeah,
Oh.
neurons and units are interchangeable.
Okay, thank you.
So I'll do it as like, I'll do the activation and then I'll do the index. So that's the trick from like lab 8 from 180 or something, where after this, I can just sort them. And now the top 10 activations are for axes at indices. And so on. Okay. No, I probably don't want to actually print the axes, just want to print the indices.
How does it sort if every element is a tuple?
So it sorts by, so when you're sorting tuples or lists, you're sorting in alphabet in lexicographic ordering, so like dictionary ordering. So it sorts, so if there is, so without ties, it just sorts by the first element. If there are ties in the first element, so like if it happens that two X's give exactly the same activation, then tie goes to the lower, the higher I, right? Because we're sorting in
Oh.
reverse.
Yeah, so it just like by default sorts for the first one, and then if it's a tie, then
Exactly.
you go to the second one.
Exactly. So it sorts basically by those. Yeah.
Okay,
So
thank
that's
you.
the same trick from like whatever lab 8 from 180. Yeah.
You said for like dynamic programming to practice like using LeetCode or something.
Yeah.
But for DFS and like search algorithms, do you have any recommendations?
So look, so the issue is that basically so dynamic programming is a technique, DFS is an algorithm. So that means that the only variation could be like in the input rather than in implementing the algorithm. So you can certainly, so for that reason, it's hard to come up with recommendations. So there was like the Q6, Q7, which I put in last year's exam, which like in retrospect, maybe I shouldn't have. But like it's kind of, so you can like come up with like any number of just like ways to define a graph. And then for each of those ways, you can like implement DFS again. But that's like basically the extent of it. Right. So
basically any variation of the question will basically just be are you able to get from some starting node to another node?
Yeah, so like there is also kind of the other aspect of it is I'm not sure if people hear the question on YouTube. But the other aspect of it is kind of looking at the problem and recognizing that you can solve it with DFS. Unfortunately, like those are kind of one-offs. So I'll tell you about like Q6, Q7 after we're done talking about everything else. So that would be an example, but like there's not like a lot of stuff out there to practice with, unfortunately. It's just like those are kind of thin on the ground. Sure. Yeah. Okay. All right. So let's maybe okay, let me
Yes. So let me maybe do let me do Dijkstra first because it kind of goes nicely with Q6. So going back to
Professor, can
Yeah.
we do use like any search algorithms? Within the question, we also have to sort of write out or define like all the data structures we're using. So like for Dexters, we have to write out the struct for like the priority queue.
so specifically the struct for the priority queue, you just cannot because we haven't covered that. In general, like there could be longer questions, there could be shorter questions. So I could say, so like one way to see it is I could say like here's like literally a picture of a graph, like implement that, right? And then maybe implement an algorithm on your specific implementation of the graph. Or I could say like here's how I define the graph, you work with that. And both of those are kind of legitimate. Right. So to be more specific about what I mean, so we had, I think in lab 9, we define kind of you guys defined the graph for the airports, right? So it could be that they say like here's a picture of the airport, so whatever it is, like do something with it, and maybe I don't give any constraints, in which case you can do whatever you want as long as it represents the information. Or I could give some constraints about how to define it. I could, in principle, again, kind of from like can only speak hypothetically until Tuesday, right? But I could, in principle, say, for example, like it needs to be an adjacency list, or it needs to be a matrix representation, or I could not say that. And I could kind of give like a part of the code and say like you must work with that, or I can not give any code at all. And like I think kind of all of those variations are legitimate, and like it's hard even to say like which way is more difficult for you guys, because like if you have the flexibility to work with whatever kind of fits your intuitions the best, maybe that's easier. Anyway, sorry, we were gonna do Dijkstra, right? All right. Fair question. So okay, so just like to give you the big picture. So what we're trying to do is find the shortest path. So what we mean by the shortest path from, for example, A to H is a path. So something like this or something like this, where the sum of the weights is as small as possible. If the graph is unweighted, then the sum of the weights is just going to be like 1 for each weight, so like the 1 for each edge. So just the number of edges between kind of the source and the destination. The way Dijkstra works is you keep computing the distance from a given source to a new node that you visit, and then the core of Dijkstra is actually saying, okay, like if you compute the distances, meaning the shortest paths, in a particular order, you'll actually get the correct shortest paths. Okay, so the order is like this. So if you think about all the nodes that have already been visited, so this is S here, right? Then the next node that you want to visit, so by visit, we mean compute the distance to, and the distance would be the actual shortest path, is a node that's outside the visited set, but you can get to it via an edge from the visited set. And the property is that the distance from the source to some node in visited plus the edge that crosses the visited, non-visited boundary is as small as possible. Okay, so we keep adding nodes, and the way we add them is we find the node such that S, the source, is definitely visited, to U, invisited, plus an edge from an already visited node to an unvisited node is as short as possible. And then the claim is, that's a theorem that we've proven, is that the distance from S to V, meaning the length of the shortest path from S to V, is actually going to be equal to the path from S to U plus UV. So that's not obvious, because you could say, well, like, what if the shortest path is like S to some X here, and then to Y outside the visited set, and then to V, right? Like, you could imagine that that's true. It's just that mathematically, if you specifically select the V such that S to U plus UV is as small as possible, then S to U plus UV is actually just the shortest possible path. There is no way that you can like go around and find a shorter path to V. Okay. Does that make sense? So, okay. So, that's kind of, if you just look at the algorithm, it's not necessarily super efficient, because what you're saying is keep adding nodes, keep visiting nodes, and then in order to select the node to be visited, maybe you need to look through all the possible nodes that you could add, right? There could be a lot of them. So in general, you could imagine that you first need to look through n nodes, and then n-1 nodes, and then n-2, and so on. So it's O of n squared iterations, where n is the number of nodes in the graph, right? So that could potentially be very slow. So the idea with the priority queue is you say, okay, rather than like from scratch looking through all the nodes that I haven't visited yet and seeing which one I need to add such that S to U plus UV is as small as possible, what I'll do is I'll maintain a list of nodes that are neighbors with nodes that are visited, together with the S to U plus UV. If I just visited U, I just keep track of like, I could visit V through U, and that would cost me S to U plus UV. And I write it down when I visit U, right? In the same way, when I visit X, I'll say, well, like if I want to visit Y through X, then it'll cost S to X plus XY, right? So I just write those things down as I visit U, and then I visit X, and then when I visit X, I add Y together with the cost of S to X plus XY. So the reason this works is that it's possible to do a priority queue efficiently. So here, the priority would be the cost of getting to V from S through U, getting to Y from S through X, and so on. And then the node that they need to add next is the first node in the priority queue, where the priority corresponds to the cost of getting to it, because that's what I want, right? I want the unvisited node such that getting to it from a visited node is as cheap as possible. Does that make sense? Okay. So that's all it is. So let's go to the implementation from class. Right. So what we're doing is we're saying we'll start the priority queue, right? And the priority queue initially is going to have the start node, and it's going to cost 0 to get from start to start, because to get from start to start costs 0. And then what we keep doing is get the first node from the priority queue, right? So then just unpack it, right? So current dict is going to be, the actual node, and you also need to just record where you got to it. So I'll get to it later. And then we say, okay, we are visiting current, and then for every neighbor of current. So this is how we get neighbor. If the node was already visited, we just ignore it. If it wasn't visited, then we push with the cost of going from current to this node, plus the distance from the source to current. So that's the priority, right? So that corresponds to S to U plus UV. Yeah.
What's the heap queue heap pop?
So this is just how you interact with priority queues, right? So you're starting it is just a list, and then here you just add like this with like priority, and then whatever it is, that's the contents.
So we don't have to code like a priority queue.
So you do not know, unless you look it up, how to code an efficient priority queue. We did do a priority queue in class that wasn't efficient.
Yeah, I was gonna say, because I know
Yeah.
there was one like on the exam a few years ago, like.
Yeah.
Okay,
Actually, I don't remember that, but would be, yeah.
it was on.
Yeah. Was it like, I think it's like, if it was me, I don't think I ever asked for like a heap implementation, right?
No, it just.
Yeah.
Just not so component of priority.
Yeah.
Yeah, I mean, that's completely legitimate, like we actually did it in class.
Yeah, that's why, yeah.
So like you could like either do something like this, like if that's allowed, of course, because that like requires you to import heap queue, right? Or like if you don't want to do it efficiently, then like it's just not that difficult. All right. So yeah, so that's kind of all it is, right? So we are saying the priority is this. So the weight of the edge to the neighbor plus the distance to the start. And then we that's the contents. So it's like the node, so con for connection. So the other nuance here is that we need to, if we want to be able to recover the path and not just have the cheapest cost, we need to actually keep track of like what is the previous node. So like what is the U? So if we're thinking about this picture, then if you have a cost of getting from S to V, that's associated with going through U, right? And we need to keep track of that, because if we don't, then there's no way to recover it. So what we do is in the queue, we actually have this object where we have both the node
and we keep track of the previous node that's associated with this cost is current, right? So again, what we're doing is we're visiting current, and then for every neighbor of current, we are saying to get to con.node at this cost, you would go through current.
Con node means the node that the one we're looking at is connected to.
Yeah. So like the way it works is we have a list of connections that's associated with each node, and then a connection has a node and it has a weight.
It's just confused because when we're doing the loops, we're doing for con and current dot connections. Does that have anything to do with the class like capital C con?
Yes. So the way we built this graph, right, is if we want to connect YYZ to LAX, for example, then we append this kind of deal to connections.
Thank
Yeah.
you.
So like this representation is like the adjacency list representation, but without linked list. Like we're using
So this is not exactly the adjacency list, because an adjacency list, at least kind of like as defined in the slides, actually stores the connections as a linked list. Here we store the connections as an array.
but that's like the main difference.
Say again?
But that's like the main difference between
Yeah,
these
that's
two.
the only difference. Yeah.
Okay. Thank you.
All right. Okay. So sorry, I forgot who did you ask about the extra? Are you okay now? Okay. Okay. That's great. All right. If there's no other questions, I'll do Q6, Q7, I guess. See ya. Bye.
Could I ask a question about A star?
Okay.
So like how do we implement the heuristic function?
So that depends on what the heuristic function is, right? So if you have some kind of information about so here, like that's a good example, right? Because you have airports, right? So if you if you also know the coordinates for the airports, so let me.
So like we just find the distance between the two airports kind of thing.
Yeah, exactly. Yeah. So if you had this, then like in here you would also add like the distance between the airports.
Right. So like the weight plus the current distance plus
Well, so it would be like, so with A star you're looking for a destination, right? So like what you would have is like, so like let's say you're looking for like distance to EWR or something. And then that would be like so like if you could compute it, right?
Right.
So if you could compute like, so EWR is like Newark, right? So if you could compute the distance to EWR, then you could say, I want to prioritize shorter distances to EWR.
Oh, okay. Thank you.
Yeah. All right. Other questions? All right, let's do Q6. So the basic idea with Q6 is you can think about
sorry, to remind people, so the question is like this, right? So it's like raised to 21. And the first person who gets to 21 is the winner. We start at 0, and then you could go to like 1 and 2 and 3, right? And then from 1, you can go to 2 and 3 and 4 and so on, right? So you can think about the game as this graph where positions are connected. If there is a move from 0 to from this position to this position, they're connected. So there's no move that gets you from 0 to 4, so they're not connected for that reason. Right? So if you think about like depth first search, like what does it mean? So you're thinking of, okay, like can I find a path from 0 to 21 such that I also win? And depth first means that what you want to do is kind of go as far away as possible from the initial position to 21 at first. So that's basically the same as the recursive search for the recursive is win, which we did in ESC180, right? So essentially you're saying just, here is winning position. And you're saying here, I want to try every possible move. And then if the position they put my opponent in is not the winning position, then it won. So that's why, like, if you find a move such that this position is not the winning position, then you return true, because if you can get your opponent to a losing position, that means you win, right? And that was like an acceptable answer, because it is depth first, because what you're going to do is you're going to go from 0 to 1 to 2 to 3 to 4 to 5 and so on first, right? Because you keep calling is winning position plus 1. Does that make sense? Now, if you want to know like how many moves, then you need to do it somewhat kind of in a somewhat fancier way, right? So here, in addition to returning whether it's a winning position or not, you would also return the number of moves needed to win, kind of the smallest number of moves needed to win, right? And here, the way you're doing it is you're saying if it's not the meaning, so either way, you just like take the minimum number of moves needed and you return that plus 1, right? So you got num moves from is winning position and moves. And then you just add 1. If there are different possibilities, you return the possibility that corresponds to the smallest one. This should be actually over here. Yeah. So this is min moves. Yeah, so we did this. So here there's actually a bug. So really we should do it like that, right? So here, what we're going to do is we're going to return true and the minimum number of moves that are needed if we're not winning, and otherwise we are returning false. Does that make sense? So, okay, so now, like, if we want the minimal number of moves, we can just try every possible move, and like if we start with 3, then that would lead to the best move, to kind of the shortest victory. Does that kind of make sense? Okay. So now, part B. So like what was really enough is just basically this, right? So like just the thing from class. So I think we did it in 190 rather than in 180 last year, which is why it was like a more legitimate question. So now, if you remember, you can implement depth first search without using recursion, right? So the way you can do it, and it's kind of annoying to do, is by having a stack of the things that you would explore. And the way you work is you say, if I'm in this position, add this guy to the stack, add this guy to the stack, add this guy to the stack. And then keep getting positions from the stack and exploring them. Does that make sense? So we start with this kind of stack. And then while there is stuff to explore, meaning there's stuff in the stack, so there's like memorization here, which is not mandatory. This is all posted on Piazza. So what we're saying is explore. So what we're saying is put next position, which for every possible move, put next position on the stack. Okay. So then we do the same thing, right? So we explore the position and we see what gets us the smallest possible move. Does that kind of make sense?
When I was doing some past exams of depth research, I was running into problems with figuring out whether, like, when you get to the bottom of one path throughout
Okay.
the graph, and then let's say you're trying to find the shortest one, so you try like the next path, it might not start from like the more you try, they're not necessarily starting from the very top anymore. You know what I'm trying to say?
I think so. So I think what you're saying is like you get to 21 first, and then what you would explore next is like somewhere here. It doesn't like start from 0 or something. Yeah. Right. So this is why we have this is why we have like the accounting for the number of moves, right? So here what we have is so we append the current position and we also keep track of what the path actually was. So in order to get the so when we get the number of moves, this is in results. So where are we appending to results? So here, what we're doing is we're appending this guy, which is the number of moves that's associated with this position. So we like keep track. So like you're completely right. We don't start from the top. So we keep track. So one way of saying it is like if we're here, like we keep track of how many moves to get to 20. And then to get to 21 is like this plus 1.
As you go to each layer, you're figuring out like what was the shortest way to get there.
Yeah.
So it's steps problem.
Yeah, a little bit. Yeah. There might be people on YouTube. I don't know. Yeah. So
So yeah, so like because of that, I'm gonna finish up the presentation, which is gonna be kind of short, but yeah. The next idea is we do kind of the same thing, but with Dijkstra. So that means that we're looking at this graph and we are trying to figure out the shortest path from 0 to 21 with the additional constraint that it needs to be an actual winning path, if that's possible. So, and that took like a little bit of work, but so essentially what we're saying is, okay, so the priority that's associated with the priority that's associated with the node to explore is just like the old distance plus 1, because you made 1 move. And then you also keep track of whether it's your turn or not. So if it's not your turn, then that means that you're not actually winning. So here, if it's not your turn, you're losing. If it is your turn, you're winning. If the position is greater or equal than 21. So that's kind of, again, like it was like not a reasonable question to ask in retrospect, because we're not even done yet. This is just Dijkstra. This is not a star. However, to make it be a star is not that difficult, because it's just changing like literally 1 line, right? So in addition to keeping track of the distance, you also have a priority, which is basically the distance, except it's the distance plus heuristic. What would be a good heuristic for whether you're close to winning? Well, how far you are from 21 would be one. And that is basically what we're using. So we're doing like basically how far you are from 21. So it's like fancier than that, but if BOS is close to 21, it's smaller. So yeah. So that's basically it. I think this is so this is like the best paid Claude.ai. So like the best thing that you can probably get on the internet, and it absolutely did not solve it. They had to like fraud it quite a bit. So yeah, so like so the first thing it gave like outright incorrect outputs, and it had like infinite loops a lot. So yeah. Claude.ai cannot get 100% in ESC190 this year yet. So yeah.
The dictionary's question from I think 2023. And I couldn't do it. I kept getting 3 when I knew the answer was supposed to be 5. So then I asked AI if they could figure out where I got it wrong. And it was just so confidently giving me just crazy code that didn't make any sense.
Yeah. What was the dictionary question?
It was the friends. So I was
okay. Yeah. Yeah. So like generally, like if you give it enough hints and stuff, and like but yeah, you got the check. Yeah.
I think I'll stick to myself. Thank you so much.
Yeah. See ya. Have a good one. Okay, that's good.
Have a good evening.
Bye. See ya.